Okay. So there are two examples of current series feedback. See, I am not going to explain what is the other topological name for current series feedback, which you should be very familiar by now. So current series feedback, we have two examples. One is common emitter amplifier with an emitter resistance RE. So when they say specifically common emitter amplifier with emitter resistance RE, you will not have a bypass capacitor. The bypass capacitor is usually put to eliminate the effect of this RE. So if you remove the bypass capacitor, it becomes an example for current series feedback. Okay, so that is how I think you would have done in your lab also. With capacitor, you would have taken without feedback. Without capacitor, if you do, it is going to be with feedback. Okay, and the equivalent of this common emitter amplifier, in fact, is going to be common source amplifier with a resistance RS. So the same experiment, if you do, in fact, with CS is going to be without feedback, and without CS is going to be with feedback. So we are going to analyze these two circuits and find what all the parameters of importance. See, current series, the current represents your output side, okay, and series represents your input side, okay. So output, I'm going to measure current, and input, you have to see what gets added in input. So voltage gets added, what gets added in series. Okay, voltage gets added in series. So output is current, input is voltage. So the ratio, if you take I by V, so this amplifier is going to be a transconductance amplifier. So you will be finding what is called as GM. So first, from the name, you have to identify what amplifier it is. So current series feedback, I'll explain once again how did I get that. See here, this notation current series mean the first current indicates output, series indicates input. So output la I am having current, so that is already I'm having the parameter. Input side series, see usually output la you will see what is same, input la you will see what gets added, because input la I'm mixing it, right? So output I have current, input la in series what added. By Kirchhoff's voltage law, a voltage gets added in a series connected components. So input I have voltage, output I have current. So the ratio is current by voltage. So it is going to be transconductance amplifier. So even though this amplifier will also have a voltage gain AV, it is more logical to derive the expression for GM and GMF. Okay, that is going to be the very, very important parameters for current series feedback amplifier. So you see a conventional common emitter amplifier. I am not going for any difficult biasing. I am having a load resistance RL in the collector side, and emitter side is not directly grounded. I am going to have this emitter resistance which is going to act like a feedback. An output I measure across the collector, and this emitter resistance across RE, I'm going to measure the feedback voltage. See, this RE is common to both input and output, so this RE will act like the feedback component. So I have an AC source Vs, which is going to have an internal resistance Rs, and I have VCC, which is going to fix my Q point for my